Great, thank you. Thanks for all getting up early this morning and coming to hear my talk. And I've really enjoyed the conference thus far, so thanks for inviting me. So, of course, everyone in this room knows that we can use chemical shift prediction to help facilitate the interpretation of NMR spectra. You might do this in terms of just simply trying to help assign some of the peaks in your spectra, or you might get into some sort of more involved crystallography example, maybe testing out different possible structural model hypotheses. And so you might have a series of candidate structures, predicting the chemical shifts for those, and compare them against some experimentally taken spectra and try to find the one that gives you the best match, which is then hopefully the correct structure. Now, in this sort of process, obviously, the more accurately you can predict those chemical shifts, the greater the discrimination you're going to have between the correct and incorrect structural models. So in the solid state community, many of you in here who are in that field have probably used CASTEP or similar codes with the GPA approximation for plane wave DFT. And so this is a model that works very well, right? There's a huge number of successes in the literature from GPA calculations. Now, typically these GPA calculations are employing the PBE density functional, which is a so-called generalized gradient approximation functional. So on the tier of Jacob's ladder, this is near the bottom of the ladder of sort of classes of functionals, with higher tiers being considered more accurate in general. And so over the last several years, my group developed these fragment approaches as a way to try to do better than that. And so in brief, the idea of these fragment approaches is saying, rather than doing a pure periodic calculation on our unit cell of the full crystal, we're going to instead do some sort of cluster model. And then we're going to focus in particular on but rather than doing that sort of big cluster calculation, we're going to focus on, for example, the molecule in the asymmetric unit that we're interested in. We're going to calculate its chemical shieldings. And then we're going to calculate its interactions and how the chemical shieldings change due to other molecules in the lattice in a pairwise fashion. So we'd calculate that dimer and get an increment to its chemical shieldings. That dimer, get an increment to its chemical shieldings, and so on. And we'd sum over all the local dimers until we get an overall pretty good picture of the chemical shieldings and how each of those dimers influences the central molecule. Now, that, of course, lacks some of the cooperative polarization effects of the lattice, longer range contributions, and so on. So then we do all those calculations in an electrostatic embedding field that polarizes everything and therefore captures some of those missing long range and many body effects. For a while, we were doing that with various self-consistently polarized point charges. More recently, in this 2020 paper, we found that actually you could do all these things rather than these fancy embedding models that we had been developing. You could just turn on the standard polarizable continuum model that's found in Gaussian or whatever your other favorite software package is, and it works just as well. So those things all work well, but I actually don't want to focus on this stuff today. I just want to make one main point from this and one conclusion that came out of this research, as well as some research that was being done by others at the time, is that hybrid functionals, which are a higher tier on that Jacob's ladder of density functionals, provide clear benefits over these GGAs in terms of the accuracies of the chemical shifts. And so here's one example. I'm showing 3 polymorphs of acetaminophen. This is actually a sort of probably a little better than average example for the performance, but you can see for these 3 polymorphs, you can see in red my predicted chemical shifts for these with GPA PBE, and then if we switch to the hybrid functional with our fragment approach. So you can see there's a nice improvement in the accuracy of those chemical shifts. And then over here in the RMS errors, you can see it. In this case, it's about a factor of 2 improvement. Like I said, that's better than usual. More typical would be something like a 30, 40% improvement statistically for the chemical shifts. You can see that here. So we, at one point several years ago, did a whole bunch of benchmarks across a large number of crystals for hydrogen, carbon, nitrogen, and oxygen. And in green, we have GPA, PBE, RMS errors from those test sets. In red is our fragment approach with the hybrid functional. So again, you can see often it's something like 30, 40% type improvement for these. So this is, I think pretty strong evidence that these hybrid functionals can work considerably better than the standard GGAs. But maybe you're not really motivated to figure out how to do all this sort of fragmenting and so on. It just seems like a lot of work. GPA is nice. You just give it your crystal structure and go. So what can you do that's a little bit easier? And so in the first part of my talk, I'm going to talk about a very simple approach that any one of you could achieve in really just minutes that allows you to correct those GPA results and get results that are on par with these hybrid functional results, or even sometimes a little better. And then the second part of the talk, I'm going to shift gears a bit and talk about a machine learning approach on how we can try to get some really high accuracy chemical shifts by correcting lower accurate ones. So I won't spend a whole lot of time on this, but again, I think this is perhaps one of the more valuable take-home messages today is if you're doing GPA and you like it and you just want it to be a little bit better, this is something you can try. So the basic idea is that switching to a hybrid functional with GPA in the plane wave basis set is really expensive. It's something like a factor of 10 or more expensive than the GGA, which is why people don't do it. But if you want to get the same benefits, you can run your GPA calculation like you do today. And then all you need to do is extract, for example, the monomer and the asymmetric unit if you're doing something like a molecular crystal. And then you calculate the gas phase shieldings with PBE. And you calculate the gas phase shieldings with PBE0. And then you just take the difference between those two and add it on top of GPA. And then you effectively get what are on par with hybrid functional quality GPA chemical shifts or shieldings. And so, and if you don't like gas phase, or if you have maybe some charged species or something, you can potentially also do these in polarizable continuum embedding. That can even work a little bit better. Most of the time it's not necessary, but it doesn't hurt. If you're doing some sort of extended system, you might just think of treating a local cluster of your atoms for this gas phase correction instead of an isolated molecule. But you can basically adapt this to a lot of different scenarios. And when you do that, here I'm just going to show some sample data. Our paper has a bunch more sets in this paper. And then my former student, Josh Hartman, has done it recently for EFGs. Same thing, it works really well. But here's some data for, again, a set of nitrogen-15 chemical shifts in molecular crystals. These are violin plots, so basically showing the error distribution for GPA, mean absolute error of around 4 ppm. Our fragment approach with PBE0 dropped that to a little under 3 ppm. But here, all these ones are these monomer corrected GPA. So I just did the GPA, and then we did the difference between PBE and PBE0 in the gas phase for the isolated molecule. And you might say, well, what basis set do I use? The answer is it doesn't really matter. Pretty much any basis set you want, as long as it's at all plausible. So all you need is something like Gaussian or an equivalent package that can do chemical shielding calculations, run your GPA, grab your monomer of interest, and then run 2 more calculations that are probably just going to take minutes compared to the many hours you spend optimizing your crystal with GPA. Calculate those shieldings in 2 different functionals in whatever basis set you like, and then add that correction onto your GPA and get these nice benefits. Here's a little more data. These are carbon CSA data that it's a little blurry, sorry. And it's basically telling the same story. You can see, again, the hybrid functional gives a much more sharply peaked error distribution than the GPA PBE, and you can achieve that same quality result by using the monomer correction approach. And it's, again, independent of basis set, effectively. All right, so that's all I want to say about that. But again, that may be one of the most valuable take-home messages from today, because it's something that's so easy to do. But now I want to talk a little bit about machine learning. So we heard a beautiful talk from Manuel Cordova and others on the Monday morning session about some of the really great things you can do with machine learning. He mentioned, for example, this example of doing the de novo crystal structure determination, combining crystal structure prediction with the ShiftML model to help solve these crystal structures. So there's a lot of really exciting things going on with models like ShiftML and so on. So if you want to say, well, what are the big challenges we'd still face? I'd say the 2 big ones are the accuracy of these models. How well do we predict the chemical shifts? Are we truly getting DFT accuracy? And then, of course, the applicability, in the sense that machine learning models are good at doing things like what they've already learned. They're not good at really extrapolating. And so really getting enough chemistry into the training sets of these is going to be a challenge, though it sounds like from what Manuel said on Monday that they're already making a big push on that to expand the applicability of ShiftML. What I want to focus on is the accuracy piece. Can we really achieve DFT accuracy? And I would argue that today, well, as good as the models are, and it's impressive how much progress has been made, that we're not truly there. So this figure is a bit of a, unfair or apples to oranges comparison. Because what I did is I basically took different machine learning models from the literature and whatever error statistics they reported, But these are not necessarily all calculated on the same system. Some of these are molecular, some are solid state crystals, and so on. So there's a bit of a mix. So don't take anything on this figure literally, but I just want to give a sense of where things are today with some of these different models. And so I have 4 different ones. Here's ShiftML. Here was some early work from Rupp, 3D DenseNet from Teresa Head-Gordon, this impression model, and so on. And in these brown bars, I have basically what are the best sort of results we obtained from, say, our hybrid density functional fragment approaches that I was just talking about a few slides ago. So for hydrogen, the gap isn't huge. But when you start looking at some of these other nuclei, you can see there's a pretty significant gap between the ML models and the sort of quote unquote best you can do with DFT today. It's something like the ML models are 2 to 3 times larger than these errors that you get from a good quality DFT calculation. So can we do anything to address that? So if you think about, so the way most machine learning models work, at least the pure ML ones, is they use some sort of local descriptor that describes the local environment of the system and uses that to infer the chemical shift. And this fits very naturally with NMR, right? It's a local descriptor. We know it's useful for identifying functional groups, things like that. But it's also modulated by the longer range electrostatics. For example, we all know, or many of the people in this room know, that the locally dense basis set approach works, right? That you need to focus with a good basis set on the atoms of interest. For the longer range, you don't necessarily need to model it perfectly, but you need to do something to capture it. So you can get away with using smaller basis sets in a large cluster or something like that. And so our idea here is to try to sort of combine this good description of the local environment with some sort of longer range but explicit description of those longer range interactions that are missing in present day machine learning models. And so the way we do this is with something called a delta ML approach. And we didn't invent this or anything. We just are applying it here to the context of NMR. But the idea of a delta ML approach is, rather than us trying to machine learn directly from, say, structure to shielding or shift, we're going to start with a cheap, crude calculation of the chemical shielding, and then we're going to try to machine learn a correction that brings that one up to the quality of a higher level calculation. And so we'll do, in this case, some really cheap DFT type calculation, add on an ML correction to our shielding that gets us something that's hopefully on par with the accuracy of our DFT. And so to do this, we're using something called the atomic environment vector. This is one of many, essentially there's variations, but they're nearly equivalent descriptors that describes the local atomic environment. It has a 5 angstrom window. So essentially, if we're talking about this atom of interest, all these atoms and balls in this drug molecule would be what are included in that atomic environment. So we get a good chunk of the molecule. But then by using this cheap small basis calculation, DFT calculation on the whole molecule or the whole crystal or whatever, you end up capturing some contribution from the rest of that molecule in the machine learning or the overall final prediction that would be missing in a traditional pure ML model. Now, for the work I'm going to show, our target was to use a moderately large PBE0 basis set, or functional with a medium large basis set. And in the end, this sort of delta ML approach is going to be 1 to 2 orders of magnitude faster than that sort of corresponding DFT calculation. Now, that's actually much slower than something like ShiftML. ShiftML is essentially instant, right? We have to do a cheap quantum calculation. So there's a trade-off. We're going to get considerably higher accuracy, but the trade-off is it's not nearly as fast as ShiftML, but it's still 10, 50 times faster than your traditional DFT. So, it depends on the application whether the improvements in accuracy are going to be worthwhile for the moderate cost. So as I said, we use this atomic environment vector. I don't want to get too much in details. Basically, it's discretizing space into radial and angular bins, and then adding some Gaussian weight for each atom, depending on its proximity to those bins. We're focusing more on proof of concept here. So we trained on a bunch of small molecules, basically all possible molecules containing up to 8 heavy atoms within HCN elements. And then we tested on a bunch of moderately larger molecules from this so-called GDB17 set. Oops. The overall approach, again, I don't want to get too lost in the weeds, but it's a fairly standard 3-layer neural network architecture, so nothing too fancy there. we're doing a so-called ensemble model. This is important to some of the things I'll mention, which is the ensemble model is rather than just training a single neural network, we end up training 10 different neural networks that are just going to end up, they each have the same structure, but they're just going to end up with different optimized parameters because it's a complex, many dimensional optimization. And then we're going to take the average of those values to get our final shielding prediction. That sort of ensemble can help improve the accuracy. And in addition, we're going to use the standard deviation among those different members of the ensemble in order to get something about the uncertainty of our predicted shieldings, which I'll come back to. But anyway, so we run our neural network model, we get our average correction, we combine it with our cheap DFT shielding, and that gives us our raw final one. Here's some basic data just to give you a sense. You can probably focus primarily on the testing column here because this is, this is what we fitted on. This is the data that's independent of the fit that we tested it on. The main things I'd point out from all these numbers are, one, if we forget the delta ML, just do the pure ML, we get an RMS error in our molecules of about 4 3/4 ppm, which is sort of on par with a lot of the other pure ML models. So basically saying, all right, it's a different descriptor, but it's not really any better or worse than the other descriptors people are using. But if we then start pairing it with various really cheap DFT calculations, you get some nice improvements. So here we paired a couple different functionals and the worst possible basis set you could use in quantum chemistry, STO3G, and already that cuts the errors in our predicted ML shieldings in half. If we go to something slightly larger, 631G, this is still too small to even that you would ever be able to publish a real calculation with because it lacks those polarization functions of 631G star. But so it's a really small basis set. But by the time we do this, you can see we're now getting sub-ppm errors in our machine learning model relative to the target DFT shieldings. If you want a sense of sort of what the machine is learning, in blue I'm plotting what the cheap shielding, the error, distribution of errors for the cheap shielding relative to the target, and you can see in particular for things like nitrogen and oxygen, there's some pretty substantial and non-uniform errors. And then in orange is what happens after we calculate the delta ML. So it's the machine is figuring out how to correct all these large errors and get down to something that has much more tightly controlled errors. If we then look at all the different nuclei and compare the error statistics, what you'll see is that the errors from this delta ML model with respect to the target DFT shieldings are considerably smaller than the sort of errors we would expect from DFT itself. So our red lines here are much smaller than the height of those brown lines. So ideally what this means is that we're going to be able to predict those DFT shieldings with this delta ML approach without introducing any significant new error in terms of our final predicted chemical shifts versus experiment. And to see that, we took just, again, sort of in the proof of concept sense, we took just a fairly small set of 9 solution phase drugs and with 114 carbon-13 chemical shifts, we trained a chemical shift referencing line on a different set of small molecules. It basically was perfectly parallel to the DFT line. I just took it out for the sake of time today, but it basically looks like a spot-on match. And then here's the overall error distributions for the target DFT and then for our delta ML, and you can also see the RMS error. So basically, our delta ML is introducing maybe a 1/4 ppm larger RMS error compared to the pure DFT. So this is showing that you can essentially not give up almost anything in your DFT accuracy while still saving this factor of 10 or more in the cost of your chemical shielding calculations. Now you will say, okay, well these errors are somewhat larger than those best errors I commented on the slide before, but that's because these are solution phase ones. We actually didn't include any solvent effects in any of the training data here. We just sort of tried to correct for the solvent in our final regression. We didn't look at any dynamics and so on. So there's reasons why this isn't the best, best possible accuracy. But I think this is suggestive that this sort of approach can give you those really high accuracy chemical shifts. Finally, I mentioned with our ensemble model, we can get the standard deviation among the predictions of these different members of the ensemble. And so, one of the big challenges with ML models is, as I said, they're really good at doing things that are similar to what they've already seen before. So, but how do you know when they're doing well versus when they're getting outside their comfort zone and extrapolating too far and therefore giving you nonsense? What we found is that we can use this standard deviation among the members of the ensemble to gauge the uncertainty of the machine learning prediction to the uncertainty in the predicted shieldings. And so, by studying the relationships between the errors between the ML predicted and the true DFT shieldings, and then the standard deviations of the ensemble, we were able to generate these curves that sort of where we sorted them by error. And you can see basically things like this, where we found that if, for example, the uncertainty in our shielding calculation is less than 1/4 ppm in this terms of the standard deviation, with 95% confidence, we're going to have errors of plus or minus 1 ppm in our ML predicted shielding, and so on. If we have a slightly larger uncertainty, that 95% confidence value might jump up to 2.5 ppm or whatever. But so we can use that uncertainty to quantify how confident that ML model is in the chemical shielding. And again, we went and tested it on that drug set, which is independent from what we used to do this analysis. And we found in that case that 94.7 of the 114 carbon-13 shieldings fell within the 95% confidence intervals we found from this data set. So I think this sort of, whether or not this ends up being the best way to do uncertainty quantification, we'll see over time. But I think this idea of trying to build in uncertainty estimates into our predictions is important. All right, so with that, I'll summarize and say, if there's one takeaway message from today's talk, it's that you can do better than GPA type calculations by switching to hybrid functionals, and it doesn't have to be hard to do so. So it's, like I said, things like this, GPA plus the simple gas phase correction can work really well. It doesn't take much computer time. It doesn't take much human effort. So it's worth doing. You can also get involved in some of these other fragment approaches, but I realize, many people already have their workflows established. So if you want to stick with your workflow, that first approach is probably the better one. And then second, well, again, I think there's been a lot of really beautiful work already done with machine learning models, like what we heard on Monday from ShiftML and some other talks. I think there is still room to try to improve these models to get higher accuracy overall. Since I've gone long, I'll just stop and thank my former student, Josh Hartman, did a lot of the early work on this, but most of the things I told you about today were done by my current student, Pablo Unzueta. And then also that monomer correction was done with a lot of input from Martin Drzecinski in Prague. So I definitely want to thank him as well. And thank all of you for your attention.
Thanks, Greg, for a great presentation. So questions for Greg. Please find your way to the microphone.
Greg, really great. Could you comment a little bit about the differences between generating a training data set using the DFT results versus empirical? Where do we stand in terms of being able to use experimental results as training? And for some of the databases that are out there, do you have a sense of what the error distribution, how well have they been curated, and where do we stand?
Yeah, I think the biggest problem is a lot of these machine learning models really do require a lot of data. Whether we didn't do strict testing on this to see, did we really need the 300,000 carbon environments that we used in our training set to get exactly that? I think we did do some learning curves, but I don't remember exactly what they looked like. But if you looked at like how much data they're using in ShiftML or we used here, the amount of data is pretty massive. And the other problem is, if you have noisy data, it can really throw off your model. I know when we were doing this and I had my new grad student, Pablo, was first trying this, he had missed a few noisy data points that ended up really skewing our machine learning. And for a long time, we were thinking, why isn't this working? Until eventually we found these handful of outliers. And so for me, especially as a non-experimentalist, that's what worries me about trying to train on experimental data is how do you get order thousands or tens of thousands of data points from experiment, knowing that there aren't going to be some miscreants in there that are going to throw things off. And so I think that, it's probably achievable, but I think it's going to take a lot of effort from people in the community who are really skilled and able to assess the quality of the experimental data beyond what someone like I can do.
That was an interesting talk. There are a couple of questions I have. First of all, on your maximum errors, they were all more or less uniform, on the order of 10 to 12, or something like that ppm.
Yeah.
And I'm curious, was that reflected in a particular shielding element, or was it just a random distribution of those?
That's an excellent question, and I don't remember, unfortunately, since it was a few years ago that we did that paper. I suspect it was either one or a handful of elements that had the larger errors. But I don't recall for sure. I know Martin actually did go back in this data set and look at a number of the experiments. He actually remeasured some of them, and we actually got some improvements in the error statistics after he remeasured some and corrected some of the errors in the referencing or whatever it had been in the literature for some of these systems before. Because originally when we'd put together these data sets, we just, grabbed things naively from the literature.
Yeah, and the other question I have is probably a reflection of my age. I am not a big fan of DFT calculations as they relate to shielding, like Hartree-Fock, Gaussian, maybe a little bit of correlation. So the question is that you have a lot of data based on DFT. Have you gone back and ran that through or compared the results relative to something with highly correlated MP2 and whatever you want to do?
So that's an excellent question. Actually, Robbie Iolucci, who some of you may know, is actually doing a sabbatical in my group right now, and we got interested in this. So he's actually coming back and looking at this sort of monomer correction approach. Wait, I should back up. The problem with doing these things purely with those methods is just those are so much more expensive than the DFT approaches. Now, that said, the ORCA code from Frank Neza has recently implemented a lot of faster algorithms that make doing things like MP2 or these so-called double hybrid density functionals that have DFT but with a bit of MP2-like correlation mixed in, somewhat more feasible. So we're doing some tests on some of these data sets with this approach. To our surprise, it's not helping at all. It's actually performing a little bit worse than the hybrid functionals. Jonathan Yates on Monday morning also mentioned his work with the scan and revised scan functional, and in that case, it wasn't any worse, but they found that I hope I'm echoing him correctly, that they didn't really see any significant improvements in the referenced shifts. They saw maybe some improvements in the raw shieldings. They seemed to be closer to the reality, but they weren't actually, by the time you did a linear regression referencing, those benefits washed away. So far, it seems like going beyond the hybrid functionals to these MP2-like or double hybrid is going to have a similar story, but hopefully we'll have that wrapped up and published in the not so distant future and be able to say more concretely.
All right, thank you.
My impression from that electronic structure theory has been that we are okay for a fixed geometry. It's the vibrational, conformational, and other such effects that are not actually captured in the Born-Oppenheimer approximation that dominates the era. So my question is, could the success of your neural network addendum be partially due to the fact that it's maybe just accounting for all those vibrational things that DFT did not?
I mean, so in the neural network, we're not, first off, I agree. I think one of the reasons going to higher level wave function or density functionals isn't necessarily improving is we're starting to hit the limits of what you can get without accounting for things like the vibrational averaging and 0 point and so on. So I absolutely agree there. As far as the neural network, I mean, in terms of the training, our training calculations were all DFT. The starting ones are DFT, the MLs are in DFT, so none of those have any sort of vibrational contribution in them. Now, again, when we start going to compare against experiment, those omissions will be presumably contributing to the errors. And I think, for example, that's part of why our solution phase errors there were more like 2.3 ppm rather than the 1.5 ppm we get in solids. But it doesn't directly manifest into ML shieldings.
Okay, if there are no further questions, then join me in thanking Greg for a great presentation.
Thank you.
Okay, our next speaker is Jeff Hoke, and the title of his presentation is Data Meet Computation.
Morning, everyone. I'm going to tell you a relatively simple story today, but I want to start off by thanking Joanna and the committee. Organizing a meeting like DNC is a lot of work in normal times, but with the uncertainty and added costs caused by COVID, it really took a Herculean effort for them to pull it off. And we really thank you, Joanna, for pulling this off on our behalf. It's so great to see you all in person. Thanks, Joanna. So I'll start off with the acknowledgements. This is a collaboration between two teams, the BMRB team on the one side, NMR Box on the other side. You'll notice there's some overlap. But one of the stories I'm going to tell you about was a collaboration with Angela Gronenborn at Pitt. And support came from both NIH and to a certain extent NSF on this. So you all hopefully know about the Biological Magnetic Resonance Data Bank, or BMRB, which was founded about 40 years ago by John Markley and Eldon Ulrich at UW-Madison. And a couple of years ago, on John's retirement, it moved to UConn, where it sits now. You'll notice probably the most noticeable change right now is that we've gone from the logo on the left, which has a left-handed helix, to the logo on the right, which has a right-handed helix. So we've caught up a little bit with our structural biology colleagues in that sense. This is a somewhat dated slide of a snapshot of some of the content of BMRB, but we're always working to try to expand not only the size but the scope of the NMR data that's in BMRB. And we've also developed as sort of a front porch that we refer to as BMR Big, that is a way for bringing in uncurated data that we don't yet have a pipeline for curation developed for, so that if you've got some data that you'd like to get out to the community, and it's not something that fits in our current curation pipeline, reach out to us and we can potentially get it onto the BMR Big platform and give you a DOI so that it can be found easily by the community. So some of the applications, in particular in structural biology of BMRB over the years, have been to help with the development of some of these packages, TALOS, Chemical Shift Index, Sparta, curated subsets like RefDB. And they certainly have helped over the years with our ability to do sequential assignments in proteins and nucleic acids and provide insights both into structure, dynamics, and disorder. But all of these applications largely focused on general trends that could be learned from the distribution of chemical shifts and other data that are in BMRB. And so, when BMRB was small, there were a lot of these extreme shifts that didn't match the general trends that we just dealt with as outliers and ignored them. But over the years, the content has grown enough that those outliers now have statistical weight, and so that we can start mining some of those outliers to try to understand the source of those things falling outside the general trends. And so I'll tell you a little bit of a story about that now. So here's an example of a chemical shift distribution for the amide proton shift in alanine, and so things like TALOS basically use the broad shape of those chemical shift distributions. But if you blow it up a little now, you can see that we're now getting many more outliers that don't fit in the significant envelope of the chemical shift distribution, and mining those really, I think, is going to be a way of gleaning new insights from the data that's in BMRB. So the example I'm going to tell you about involves a hypothesis that was posed by Michael Levitt and Max Perutz back in 1988 that an amide, an H group, can hydrogen bond to an aromatic ring, to the p-pi cloud. And there have been many people have found examples of this in the gas phase. There's a lot of evidence from things other than NMR that this kind of phenomenon does occur. But the question we had was, to what extent does it happen in real life in the case of proteins? And we were the impetus for doing this was a question that Angela posed to us about two extreme outlier amide proton shifts that she had in her AOO lectin that she's been studying for many years, the one that has anti-HIV properties. And so she asked the question, first off, she said, are these ring current shifts that are responsible for the extreme secondary shifts that she sees for those two amide proteins, which the answer which is almost certainly correct. But furthermore, is it possible that these are involved in hydrogen bonding interactions with nearby aromatic rings? And so based on that, we wanted to go back and see how much evidence is there in BMRB and federating the BMRB data with the corresponding structures in PDB that these kinds of hydrogen bonding interactions exist in nature. So we started looking at using chemical shift to filter structures to go look at in the PDB. So I've broken it out, the distributions here. The z-score is just the difference from the mean chemical shift in units of the width of the standard of the distribution, the standard deviation of the distribution, and negative z-scores correspond to an upfield shift here. And so I've broken it out by the identity of the nearest aromatic ring, whether it's a tyrosine, phenylene, tryptophan, histidine. And at the bottom, we've just blown it up to look at the beginning of that distribution a little bit. And one of the things you notice quite quickly is that the outliers in this distribution have different characteristics. So for example, in the case of histidine, you tend to get mainly, the outliers tend to be mainly in the downfield direction, whereas for the other aromatic rings, that more of the outliers tend to be in the upfield direction. So I'm not going to belabor this too much because it's been published. You can go and look at the details, but I do want to share with you one interesting feature that came out of this. So if you look at the tyrosine distribution at the top, this is a distribution of the azimuthal angle, which is just the angle between the vector between the center of the ring and the nearby amide proton, and the normal to the aromatic ring. So it's just a question of, if it would be 0 if the amide proton is sitting directly above the aromatic ring. What's interesting is you don't see a peak in this distribution corresponding to 0. So it suggests that they're not sitting directly above the center of the aromatic ring, aligned with the normal, which is what Perutz and Levitt hypothesized. Instead, it turns out they're largely sitting directly above one of the ring carbons. So they're actually interacting. They're not hydrogen bonding to the donut hole. They're hydrogen bonding to p pi orbitals, which actually makes a lot of sense. Anyway, so that's a summary of the findings. But one of the other findings, of course, was that we found thousands of examples of potential hydrogen bonds involving amide groups and aromatic rings. And to the extent that these are hypothesized to have about 3.5 kilocalories per mole of favorable energy, these are things that if they're there, we should be including in our structure refinements for sure. So the point of this, though, was to tell you about the workflow that was done to do this analysis. And so we initially started just using the BMRB, just using the advanced search features to filter out things that we knew would screw up. So for example, we excluded proteins that have paramagnetic centers or hemes. There are a few other filters that are applied, identified, and then looked through those sets for chemical shift distributions. And then we would, by downloading the NMR star files locally to the platform we were doing the computation on, and then we would go and download the corresponding structures from PDB. And typically, after this filter, we were getting on the order of 8,000 or so files that we had to download. And then we would do the geometrical analysis and the federation of the BMRB and the PDB, the structure data locally. The problem is that it took about 6 hours every time we reran this filter to ask a new question if we wanted to look at some particular feature of the geometric distributions. And so every time we'd ask another question, we'd have to go back and wait essentially overnight for this thing to complete. There's another problem that was relatively minor given the short time frame that we were doing this, but over a longer time period, it can become problematic. If you're doing a survey of either the BMRB or PDB, they're not static. There are new data sets being added all the time. So trying to recapitulate a survey exactly on a moving target is impossible. So one of the important things is if you want to try to do surveys like this, you got to have a static snapshot rather than and be able to point to the particular time that you snapshotted. So what we did is a workaround to this 6 hour workflow was to create something we're calling the Riboxatory data lake. So it was a collaboration between the NMRBox team and the BMRB team. And what we've done is we've created those snapshots of BMR, entire public content of BMRB, the entire public content of PDB as a local file system mount on the NMR Box platform. We've also added the AlphaFold and NCBI non-redundant sequence databases on there, and we're open to suggestions for additional databases that we can put on there. And furthermore, we snapshot them on a monthly basis, so that if you want to do surveys, you can focus on a particular snapshot of those databases, so you can get consistent results. That file system is accessible to all of the 40 plus servers that NMR Box runs on. It's connected through a network that attached storage and currently a 10 gigabit per second switching fabric. We're in the process of upgrading that to 40 gigabyte per second switching fabric. But by doing this, by bringing the data locally, instead of having to do the filter and gather everything by downloading from the BMRB and PDB websites, we've reduced that 6-hour workflow to about 12 minutes. So it made it the cycle of discovery a lot more efficient. So here's just how you would access this. You can use a file browser, or you can or via shell, you can drill down through. So it's the mount point is just /repository on NMR Box, and here's just an example of drilling down. So they're archived according to time of the snapshot. So you can choose the year, choose the month, then the content appears there as you drill down further. It turns out this is small data, so it's not a huge burden for us in terms of storage restructures. Now, if you want even more speed, there are some other things about NMR Box that I hope people will be aware of and make use of. We have NVMe solid-state drives attached locally to each of the NMR Box servers. The mount point for that is just Scratch. So if you want something that involves a lot of I/O or a lot of file operations, move your data over and do the computations on /Scratch on NMR Box. And this is particularly useful for example, if you're doing multidimensional data processing using NMR pipe, because it does a lot of file operations. And that'll be speeded up tremendously if you move your data over to Scratch. We're getting read-write speeds that are pretty awesome with those NVMe solid-state drives. But if you want to be even crazy fast for computations or analyses, all the NMR Box servers have large amounts of RAM. Some of them have absolutely massive amounts of RAM. We've got some of them have more than a terabyte of RAM available. So in fact, we're going to be describing shortly some tools we've developed for doing geometrical analyses on processing of PDB, where we've loaded the entire content of PDB into RAM. And it's just crazy fast when you do that. So I want to close with two announcements and a request. The announcements are we're running our summer NMR Box workshop that's been on hiatus due to COVID. Well, it was virtual due to COVID the last couple of years, but we're going to be doing it again in person, June 6th to 9th in Farmington. And if you're interested or have students who might be interested, we'd be delighted to have you come and join us. There's no cost other than the travel expenses and lodging to join us. This year, we're going to have Charles Schwieters from the NIH as a guest, who's going to spend a day doing a tutorial on using Explore NIH. And we're also going to have a team from MathWorks who are going to do a deep dive on using MATLAB. The other thing other announcement, UConn Health is seeking an NMR facility manager at the position's open rank. If you know of anyone who might be interested, have them come and talk to me. And now I want to close with a request. The bottom line is that it appears that NIH support for BMRB is going to come to a close next year. And we had this just last Friday, a statement from a program officer, very carefully worded. He says, NIGMS does not view NMR as significant. So if you have used BMRB or you value BMRB, My hope is that you'll reach out to us. Just send an email to support@bmrb.io and let us know if you'd be willing to write a letter of support. We're hoping to just inundate NIH with more letters of support than they care to read. And with that, I'll close. Thank you very much.
Jeff, for a great presentation. So questions for Jeff, please make your way to the microphones.
Spent too many days behind a computer. There's no such thing as upfield or downfield. The other thing is that this goes back a long time for you, but the fact that this proton is sitting over a p orbital is actually a good idea. The trouble is that it's not static. Do you have a feeling for?
That's a great question, Paul, because of the degeneracy, the interaction would be the same for any, for phenylalanine or tyrosine. It should be six-fold degenerate, right? And so you might look for hopping around that. Oh man, would that be fun to go looking for? One of the other things that we're working on, Lucio Friedman is helping us out and thinking about how to get more direct evidence of this by detecting the J coupling that you would anticipate between the amide proton and the ring. Milo Wessler has done some Gaussian calculations. He thinks it's going to be small, probably somewhat less than 1 hertz. It's a bit of a challenge to look for a coupling that's that small when line widths are much larger than that, but I think hopefully Lucio has some ideas for cracking that nut for us.
Lovely talk, Jeff. Following up on Paul's question, would it be possible to predict ring flips based on where this?
So that's, I think, we'd love for somebody to do that dive because, there are a lot of inequivalent chemical shifts for two opposite sides of the aromatic ring in the BMRB. Now, some of those we think are probably maybe misassignments. So I think a curation needs to be done to be able to address that first. But once the data is curated, it would be ripe for looking at ring dynamics just based on inequivalence of the chemical shifts on the two sides of the ring. Great suggestion, Hari.
So as you alluded in the introduction, I mean, longstanding theories for ring current shifts, don't take into account the effect of hydrogen bonding.
Right.
So if you do the calculations using those theories, you see discrepancies that you would associate with the effect of the hydrogen bond interaction.
The accuracy just based on ring current shift calculations is relatively poor, but we still do at least identify them as outliers. The absolute agreement is really awful. Because clearly in the case of hydrogen bonding, electric field gradients, are much more important for amide protons than they are for other aliphatic protons for sure. But the ring current shifts do identify, to a certain extent, help you identify the outliers, which ones are going to be outliers, but they don't quantitatively agree at all.
Any further questions for Jeff? Then please join me in thanking him again. I'm really not just checking for text messages. I have the titles on here because we're staying green. Okay, our next speaker is Ilya Kruprov, who has moved from his traditional 7 a.m. session to join us in the late hours of the morning now. And Ilya's title is The Making of DeerNet. Why and how do neural networks work in magnetic resonance data processing?
Thanks, Len, and thanks, Joanna and the team for putting together a lovely ENC. It's a pleasure to be back in the saddle in in-person meetings and being terribly jet-lagged and everything else. I'm thoroughly enjoying the process. Okay, so the one question I think that neural network work quite leaves unanswered, and a philosophically problematic question that we bumped into in our magnetic resonance work is all those neural nets that we train, they're generally black boxes, right? You cannot look inside. The intermediate signaling is scrambled. And it's a serious philosophical problem because of the scientific framework of positivism, right? You're supposed to understand what is going on. And so we've encountered it, and this is a summary of our go at it. Now, since this is an NMR conference, I think I should give a brief introduction into DEER spectroscopy because that is closer associated with EPR. Now, we all know what a spin echo is, and so if we have two electrons in the system, two unpaired electrons, for example, on nitroxides in different parts of the molecule, we can do a spin echo on one of them, and there's your pi by 2, and there's your pi, and there's this little splash of an echo, except DEER spectroscopy is a spin echo that has been slightly messed with. So as you know, by default, if we do nothing, we refocus the chemical shift and we refocus all external interactions. However, if we at the same time give another pi pulse on the other electron, then we will refocus everything except the dipole-dipole coupling between them. And if we shift this pulse around, what will happen is we will give it different time to evolve under the dipolar interaction. And so we will have an echo modulation here. And that's essentially a dipole-dipole interaction frequency that is being modulated with. And there's plenty of technical refinements. Electronics is a bit tougher in EPR, so we have to work around the various dead times, various complicated artifacts. So real sequences are a lot more complicated than this. And there's much statistics on the post-processing, but that's the general idea. We've just measured the dipole interaction between the two electrons. And this is super useful because electrons are, of course, 600 times more magnetic. And so distances can be measured all the way to about 100 angstroms on a good day. This is coherent, not relaxation, so 1 over r cubed as well. In various, this biomolecule dimer in here, and you can either introduce them by mutation, or sometimes they just naturally occur if it's a metalloprotein. They can be introduced into nucleic acids as well. And so Gunnar Jeschke has written a wonderful review of the subject. This is the functional form of how that modulation looks if you just have 2-point electrons at a distance. And this is lovely because it's a bunch of cosines and Fresnel functions that we really understand quite well. Reality, however, tends to be rather messy in that firstly, you of course have a distance distribution in every frozen glass. So it's not a single distance, it's a convolution of this kernel with some distance probability density. Secondly, our pulses in EPR are never perfect, right? Resonator bandwidth is narrow, and it's very hard to give a pulse that it would be perfect because the width of the EPR spectrum, can be gigahertz. So we have this modulation depth, which is there because of the pulses are not perfect. And then, of course, the finite concentration effects, you have other electron pairs nearby that mess up the dynamics. And so there's an actual exponential decay here, stretched exponential, with the dimensionality that depends on the distribution dimensionality of your sample. Anyway, after the dust has settled, this is what we want. We want the distance distribution out, and it's buried under the layers and layers of nonsense in here. So first it's a convolution with this kernel, then there's this modulation depth transform, then there's a stretched exponential decay, and then there's noise, and this is finally what you measure. And so as you can imagine, pulling out P of R from underneath all of this mess is a seriously difficult problem. Strictly speaking, it's a Fredholm integral equation of the second kind with the addition of the noise. Anyway, so can we use neural networks to do that? Well, ultimately what we're dealing with is a noisy and messy deconvolution problem. And neural networks are really good at that because image recognition is deconvolution, right? You've got a picture of a dog and some doggedness kernel, and you deconvolve it and you get a delta function where the dog had been, right? So image recognition is a deconvolution problem. And so why would we try using them? That is because this integral here is an ill-posed and an unstable transform in the Hadamard sense. So what is a well-posed problem? Well, firstly, a solution must, of course, exist, and thank goodness it does. However, the solution must be unique. And as you know, that convolution integral, it's just like a mincer, right? You cannot undo it and rotate it backwards and get a pig back. So it messes it up. So many solutions, most of them wrong. The solution has to be continuous with respect to the input, and that is not the case as well for various obscure reasons. And a well-conditioned problem is essentially a stable one, right? So the derivative of the solution must be small with respect to the perturbations in the input. And that is also not the case. So the transformation that we have from the space of all the modulations into the space of all the distance distributions, it's not as bad as the inverse Laplace transform, but not as easy as the inverse Fourier transform. So it sits somewhere between the inverse Laplace and the inverse Fourier transform, kinda, sorta unstable. And that's an example where we have a gold nanoparticle. This is from a paper by Viktor Chechik's group that has been functionalized and nitroxides have been bonded on top with the sulfur links. And there we know the analytical solution. And this is an example of how traditional processing corrupts the data. We are supposed to have a sharp peak here and a smooth pedestal. And you can see in this case, Tikhonov regularization messed it up. So how does one go about solving such things? Well, firstly, we can only look for solutions in the class of smooth functions, which amounts to penalizing the norm of the derivative, and that's called Tikhonov regularization. Or we can simply fit a model, and if it's a bunch of smooth functions, then it is going to work. However, both of these have giant numbers of obscure adjustable parameters. These are really clunky, inconvenient methods. And for a long time, people have been looking for ways of doing these unstable transformations in a way that is nicer. Okay, so we ultimately have here a noisy and distorted deconvolution problem. I will remind you what neural networks are. A neuron, biological neuron, collects depolarization waves, and if the level of depolarization exceeds a critical threshold, it sends the action potential out down the axon. And mathematicians in 1940s have basically modeled that literally. They said a bunch of numbers come in, are getting multiplied by weights because sensitivity here differs, are getting all summed up, you add the bias, which is a measure of how ready it had been to fire, send it through a nonlinearity, your number comes out. And functionally, this is trivial, right? It's a scalar product, add a number, send it through a function. But there's a wonderful theorem about these things. For any arithmetical or logical function, or for any finite accuracy, there exists a finite neural network that would output that function to that accuracy, the so-called universal approximator theorem, which partially explains why you and I have evolved as neural networks rather than Turing machines, for example. This is super powerful. Anyway, in magnetic resonance spectroscopy, I've done some digging and some of the usual suspects have emerged. Jim Prestegard, ages ago, has actually pioneered neural networks in nuclear magnetic resonance to do the determination of protein structure. But what they didn't have at the time was the computing power, right? So the initial burst of interest in neural networks in the 80s was a fiasco because people vastly underestimated the amount of computing power that they need. They needed about 6 orders of magnitude more. And now this splash of publicity is due to NVIDIA cards, actually, chiefly because they're monstrously powerful. A single card costs more than my car. And you start getting these wonderful papers now about sparsely sampled NMR reconstruction, virtual decoupling. And you've just seen 2 wonderful talks that have been using machine learning in various ways. So now that the computers are fast enough, that works. So there's a big problem. There's not enough dear data in the world, and there will never be to train a neural network. So we must train it by simulation. We add all the reasonable noise and the distortions and the artifacts and everything. We generate them procedurally using spinach. And in our case, it's not 10,000 data sets that you need. It's about 10 to the 10 to get those networks to train. But well, we've got a big computer now. So we generate structural ensembles, get distance distributions, do the simulations, train the neural network, and then it can do our data processing. So actually training a neural net is trivially easy. It's just a glorified least squares. The principal challenge is finding enough training data. And of course, if you generate it by the simulation, you effectively have an infinite training database. And that is really quite cool. The network itself is quite simple. Vector input times a matrix. Batch norm is just a statistical trick to accelerate convergence. Through a function, again, times a matrix, through a function, times a matrix. Through a function, a vector comes out. You normalize it because the output has the meaning of the probability density, and it works. And I wouldn't bore you with the details of how it works, but it works super well. It outperforms Tikhonov regularization hands down, and in fact, most of the software that is currently out there. So ourselves and Gunnar Yeshke's group, we were quite shocked by how well the blasted thing actually works. And that then begs the obvious question, right? So here are some examples, actually. We teamed up with Daniela Goldfarb's group and Enrico Bordignon's group to get all the experimental data. So that's that pedestal that I talked about at the very beginning, and the neural network gets it right. Tikhonov regularization wouldn't have been able to, fundamentally. All the multimodal distance distributions are processed correctly. Various artifacts are correctly detected and ignored by the neural network. And even when you give it data sets that don't have any information in it, you can actually train neural network to recognize those situations and refuse to process such data. And these error bounds come from an ensemble of neural networks which just do statistics across multiple neural nets and look at the extent to which they agree. Anyway, all of this works, but that's old hat, right? We know neural networks work. The question is how. And if you look at these two chaps, René Descartes and Karl Popper, they look at us with a reproach, right? That we are abandoning the fundamental tenets of what it means to do physics, because neural network is a black box. And it is not compatible with the rational positivism framework of science. And the principal issues are interpretability and trust. So what it does and what is the measure of uncertainty in the output. Now, mathematically, a neural network is quite simple. So a bunch of vectors goes in if you send an entire database, times a matrix through a function, times a matrix through a function. But the biggest problem is, you see, intermediate linkages here are only defined up to a permutation. If you do an arbitrary permutation of that vector and the next layer undoes that permutation, that's still the same network. So effectively, the intermediate signaling is encrypted. And there are, of course, n factorial possible permutations in there. And so they're a complete black box. So how would you undo that black box? Well, you could insert a wiretap that you can say, okay, it's a transformation that discrumbles it, right? Makes this signal interpretable, whatever interpretable actually means. And our definition was that we want to make an entire database at this point output simultaneously smooth signals. And hopefully if 10 to the 10 signals are simultaneously smooth, then they might be interpretable. So, okay, I'll skip a giant amount of mathematics here. It's a monstrous exercise in the theory of Lie groups of how you find such transformations. We search them in the special, search for them in a special orthogonal group. Ton of mathematics and variational calculus later, you can actually do that. And you pick the simplest possible neural network with just 2 layers. And this discrumbler, it's an LBFGS quasi-Newton minimizer against some criterion of intelligibility, which we managed to design. Essentially all of that I will skip. This is a very long story. This is how the layer matrix looks in a neural network that has not been discrumbled. You can see completely unintelligible, right? Just basically random squeaks everywhere. After we apply the discrumbling, we start getting some patterns. If we interpret this in Fourier space, it immediately becomes clear that high positive and high negative frequencies are multiplied by 0. That's a bandpass filter. Turns out that the 0 frequency is also obliterated. So that's a notch filter that gets rid of the baseline, because the baseline is a 0 frequency signal. And then this strange hourglass shape, if you zoom into it, it's a cubic curve. And it's a cubic curve because, of course, the distance dependence in the dipolar interaction is cubic. So it's a distance axis rectifier from cubic to linear within the band of the filter. So a neural net spontaneously invented a bandpass filter, a notch filter, and a frequency axis rescaling transformation, packaged it into a single linear transformation in just 1 layer. So all of this mathematics has been spontaneously designed by the net. It's unattended training from a random initial guess. Second layer, again, an interpreted matrix looks random. Once you descrumble it, some kind of patterns emerge where, you know, faster frequencies correspond to shorter distances and slower frequencies to longer distances. But if you hypnotize this matrix long enough, turns out it's right orthogonal and left orthogonal. So the products are like vaguely diagonal. The input singular vectors are sinusoids. It's also orthogonal on the other side. And the output singular vectors look really strange. But for my sins, I teach all the mathematics at the Southampton chemistry department. And so I know that these are Chebyshev polynomials. So for some reason, and they do continue, right, if you plot more of them, it passes information using sinusoids. Actually, in signal engineering, this is called frequency division multiplexing, and it invented Chebyshev polynomials. And that kind of makes sense because the output is a combination of peaks, and if you cut the baseline of like the final transfer function does, you get these patterns of peaks. So output layer spontaneously evolved frequency division multiplexing. It drops small singular values out of it, so it's a spectral filtering regularization. Some kind of frequency distance transform in this case, and for goodness sake, Chebyshev polynomials. So if you're not shocked by now, then you really should be, because this is 15 minutes of unattended training from a random initial guess, and this thing invented half undergraduate mathematics. So that was scary enough that it ended up in PNAS. I will not go through the details of what the intermediate layers do. Jay Keeley managed to do that. It's a great pile of group theory to do with the connectivity of the special orthogonal group in that it has two disconnected submanifolds. And after the dust has settled on that analysis, it turned out that the network has jumped into a supergroup where that's a phase rotation group, which is actually path connected in order to then being able to jump from one of the images to the other here. So it apparent, I would not go into details here, but it would seem like it has invented group embedding. We were able to reconstruct the network, so we put together a combination of digital filters. That's a soft bandpass, that's a notch filter, and an approximate frequency distance transformation using regularized pseudo-inverse. And indeed, so the first layer gets rid of the noise and of the baseline, and the second layer correctly recovers the distance distribution. So we actually managed to learn something from that neural network using the method that it apparently uses. So these things that we know about, and we are quite likely to find something else too there. We were also able to teach that network to process sparse DIR data using what we ended up calling the no magic assumption. You've seen from the previous slides that it more or less invents known mathematics. So we expected that it would find some kind of interpolation or fitting process. And of course, interpolation and fitting, they share exactly the same mass. It's a matrix inverse times a vector in here. And to make it easier for it to do that mass, we just supplied all of the components that are algebraically necessary to do that transformation. And behold, it started processing sparsely sampled data. Actually, for arbitrary sampling patterns, we didn't even have to tailor the sampling schedules in here. Anyway, summary. It would seem that that's been observed by many people, that the ability to simulate may be turned into ability to interpret data using neural networks. And this descrumbler method that I've described finds out how these neural networks work, at least in favorable cases. And a simple three-layer neural net has invented sophisticated digital filters, spectral filtering regularization, Chebyshev polynomials, and topological group embedding, as far as we can tell. And so we told the funding agencies that this is fascinating and slightly scary, and they funded us, which is good. And the final thing to do is to thank the four biological neural networks, one artificial neural network and one Turing machine, that contributed to all of this. So this is my team at the University of Southampton. NVIDIA was kind enough to give us the GPUs, and Leverhulme Trust and MathWorks have funded us. Everything I've talked about is implemented in Spinach as open source documented code. If you want to see all of this, go to spindynamics.org. It's all there. And thank you for your attention.
Thanks, Ilya, for a really interesting lecture. Questions? Yep.
Thank you for the great talk. I just a question about your descrambling process. How generally applicable is it? Is it restricted to like CNNs, or can we use it for like fully connected?
It has to be fully connected, is the first restriction. So convolutional ones, it wouldn't work, but of course, fully connected are a superset of convolutional, so that's not a problem. And secondly, you need to decide what you mean by interpretable. For us, it was simultaneously smooth. For you, it could be something else. For example, in image recognition, you want some specific statistics on luminosity and chromaticity, or maybe you want your signal to be maximally local. Or maybe you want something else. As soon as you define quantitatively what you mean by interpretable, you can formulate an interpretability functional, a variational derivative of that with respect to the generator of the transformation is your gradient, and then it's the same computational complexity as the training.
Yeah, thank you.
Further questions for Ilya? Then let's thank him again. Okay, our next speaker is Owen Bessette, who will discuss structural fingerprinting of short oligonucleotide therapeutics by solution state NMR.
Hi, everyone. I'd first like to thank the event organizers for putting this conference together and also for inviting me to come here and present my research to you. And also I'd like to thank the audience for being here in person. Those who can't be here in person obviously attend virtually. So thank you for your attention. My name is Owen Bessette. I'm a postdoc at the Institute for Bioscience and Biotechnology Research, IBBR in Rockville, Maryland. I work under the mentorship of Drs. John Marino and Robert Brinson. Today I'd like to talk to you about NMR methods to structurally fingerprint short oligonucleotide therapeutics. Let me see if this mouse thing is working. Cool. Okay, so as an IBBR postdoc, my project is funded by the National Institute of Standards and Technology, or NIST, whose mission is to promote innovation and industrial competitiveness by advancing measurement science, standards, and technologies in ways that enhance our life. Within NIST, I work under the Biomanufacturing Initiative, which seeks to provide measurement science, standards, and technology predominantly for protein-based drugs. However, we've recently expanded outside the realm of just proteins to nucleic acid-based therapeutics, including mRNA and short oligonucleotide therapeutics. NMR fingerprinting has emerged as a powerful technique to characterize the overall structure and purity of protein-based drugs, including large monoclonal antibodies, or mAbs. These methods are fit for purpose depending on the size of the molecule of interest, as well as for its different class, chemical class. In the case of monoclonal antibodies, or mAbs, methyl 2D proton carbon fingerprints seem to be the method of choice, as shown here on the right. As you can see, the methyl groups are fully dispersed throughout the monoclonal antibody, and therefore any changes to its overall structural integrity can be captured by the different proton carbon correlations in the methyl region. Either in a change in their peak position or a change in their line widths or intensities. This is the NIST mAb, which is a reference material for which most of this work has been developed. The various NMR fingerprints can then be used as data sets, can be used as inputs for chemometric analysis, and then these can pick apart subtle changes in structure and purity that we might miss if we are just examining the spectra by eye. Although these methods have been well developed for mAbs and other protein-based therapeutics, an open question remains on which methods would be most appropriate for other therapeutic classes. Specifically, we want to know, can we apply the various NMR fingerprinting techniques to characterize short oligonucleotide therapeutics? So some of you might be wondering, what are short oligonucleotide therapeutics? Well, as the name suggests, they are short. They are 10 to 40 nucleotides in length, and they can be either single-stranded or double-stranded. For those of you who want to think in terms of mass, this is about 3 kilodaltons to maybe 12 or so. And short oligonucleotides therapeutics have really emerged as a new class of biopharmaceuticals to treat diseases that are currently inaccessible to the traditional protein-based and small molecule-based approaches. As you can see, the number of FDA-approved drugs of this class are constantly increasing. Right now, there are 14, but we expect them to be even higher in the not-too-distant future. In general, short oligonucleotide therapeutics can be divided into antisense oligonucleotides, or ASOs, as well as short interfering RNAs, or siRNAs. The ASOs, but in both cases, the oligonucleotide binds the complementary sequences and either silences the gene expression via RNase H-dependent degradation in the case of ASOs, or the RNA interfering pathway for the siRNAs. Also, some of the ASOs modulate splicing content. So part of the problem in developing nucleic acids into drugs is they are inherently unstable and they have poor drug delivery to target organs. So a lot of effort is placed into optimizing formulation conditions, including salinity and pH, as well as chemically modifying the nucleic acids to protect them in the cell. In terms of drug delivery, both lipid nanoparticles and GalNAc conjugation have been used to carry these drugs into the liver. Although short oligonucleotide therapeutics represent this gray area in regulatory space and that they are synthesized chemically, but they are in fact biomolecules, it's nonetheless quite apparent that the overall structural integrity and purity of the drug is of paramount importance to drug safety and efficacy. For those of you who work with nucleic acids, you are, I'm sure, very aware of the many degradation pathways that they can go through. One of the most dangerous would be depurination, shown on the right, which results in an abasic site. So these types of impurities are very harmful to the patient and need to be characterized. Although some of these other forms of degradation aren't necessarily dangerous to the patient health, they lower the overall drug efficacy and therefore should not be ignored. So we propose using NMR methods to structurally fingerprint short oligonucleotide therapeutics to aid in drug development and quality control. To do this, we designed a model siRNA therapeutic, which contains many of the chemical modifications, including 2'-fluoros, phosphorothioates, and 2'-O-methyl groups that are commonly found in FDA-approved drugs. Additionally, we have a model ASO, which the entire nucleic acid sugar phosphate backbone has been replaced with a phosphodiamidite morpholino oligomer chemistry, and that's shown on the left. For this class, we have both the single-stranded antisense drug as well as a hybrid duplex of that PMO complex to its complementary nucleic acid strand. It's important to note that all of these models are formulated in conditions that closely match those of FDA-approved drugs, so phosphate and sodium chloride, and at neutral pH. And also these are prepared at natural isotopic abundance, so no carbon-13 or N15 labeling. And all the measurements I'm about to show you were collected on readily available magnetic field strengths of around 600 megahertz. There's also some 900 megahertz, but you don't need to use that high of a field strength. As a first pass, we collect 1D proton spectra. These are very rapid experiments, but as you can see, they are rather complex and cluttered due to the poor chemical shift dispersion. The one exception being the amino region, which is kind of shown in boxes. In contrast to the large monoclonal antibodies, the relatively small size of short oligonucleotides allows for them to be readily assigned. So we actually have chemical shift assignments for these. The details of that are found in the citation on the bottom. In addition to proton, we can also collect 1D phosphorus measurements, shown here. Of interest are the phosphorothioates or PS modifications. So you see these kind of peak clusters, and these correspond to the different diastereomers that result from the phosphorothioate modification. And there's some growing evidence in the literature that the different diastereomers have different levels of therapeutic efficacy. Therefore, methods that can kind of report on the overall distribution of those stereoisomers, as well as possible characterization, will become of increasing importance. We can also collect 30 phosphorus NMR data on the PMOs. These are also have chiral centers, so there's a lot of different diastereomers in this case. But there is one well-resolved pair of signals around 23 to 24 ppm, and this corresponds to this terminal 5' PM. And what's interesting about this is that when you complex it, the line widths change. And so this is a powerful tool to be able to follow the oligomerization state in complex formation. It's been well documented that PMOs are prone to aggregation, and therefore methods that can kind of report on that are going to be more and more useful. Lastly, for the 1D methods, you can collect fluorine data. And so these are obviously introduced into the molecule to stabilize it, but these are great NMR handles. Fluorine, as everyone probably can guess, is virtually absent in biological systems, and it's also absent in a lot of buffers. So you get a really nice background-free, relatively simple spectra. One way we can enhance the resolution of these methods, as I'm sure everyone here knows, is to disperse these signals along a second dimension via a 2D NMR experiment and via spectral editing. So kind of the classic shown here is a 2D amino proton nitrogen SOFAST HMQC, and this nicely defines the secondary structure of the nucleic acid therapeutic. What's really nice about this measurement is now those immunoprotons that we saw from the 1D proton spectra are separated based on the residue that they belong to. So all your pyrimidines are shown at the bottom and all the purines are at the top, the Gs. We can do the same thing, interestingly, with the PMO when it's complex to its nucleic acid complementary sequence, and we get a nice readout of its secondary structure here. Once again, you have the same distribution of the pyrimidines from the purines based on the nitrogen chemical shift. One of the downsides of these measurements, as I'm sure everyone has probably guessed at this point, is nitrogen is very low in terms of natural abundance, and it has a lower gyromagnetic ratio. It's about 10% of a proton. So these methods are relatively insensitive. I'll scare you and tell you that we had to take like 4,000 to 16,000 scans to acquire these data. So that's quite a lot of time. The other thing is these measurements require colder conditions, so around lower than 20 degrees Celsius, and acidic conditions. So this is not always desirable. If we focus on the non-exchangeable protons, we can cut down our experiment time, and we don't have to worry about the pH of the solution as well as the temperature to some degree. So here we have a 2D aromatic proton carbon HSQC, and once again, the proton signals are well dispersed in the carbon-13 dimension into 3 distinct regions. We can now apply some of these methods to look at the more the non-natural residues of the nucleic acid therapeutics. So here is an aliphatic 2D proton carbon HSQC, and this is focusing on the 2' O-methyls. So this gives you kind of a unique fingerprint for this therapeutic class. You can also do the same thing with the fluorines. However, if we, instead of detecting on proton, if we detect on fluorine instead, we actually can get rid of any signals from protonated excipients and more importantly, water. So this is a really nice method to basically get rid of water, and we get a very nice clean background spectrum. Okay, so you're probably all thinking this is great. You've shown this on your model systems. How does this actually work for like a real therapeutic? So we then applied these methods to our simulated drug product, Givosiran. This is an actual FDA-approved drug for the treatment of acute hepatic porphyria. It contains many of the chemical modifications that were represented in the model systems. One of the new additions, though, is that this has an L6 GalNAc ligand, and this is used to target hepatocytes. So we run our barrage of 1D NMR fingerprinting techniques, and we are able to fully capture the different regions of the nucleic acid. Although, as you probably can notice, especially in the case of the phosphates and the sugar regions, these are pretty low resolution. However, they're acquired pretty rapidly, and they do provide some useful information. The 2D amino nitrogen SOFAS HMQC also shows a well-folded secondary structure shown here, and you can distinguish between the U and the G residues very nicely by the nitrogen chemical shift. We can also run an aliphatic 2D proton carbon HSQC, and this reports not only on the 2'-O-methyl regions, but now we're also seeing that GalNAc ligand as well. So this is a powerful method to also look at the delivery vehicle in addition to the siRNA cargo. So in conclusion, I hope I've convinced everyone that we can actually use NMR to get a nice structural fingerprint of short oligonucleotide therapeutics, not just monoclonal antibodies. In contrast to mAbs, the simplicity of short oligonucleotide therapeutics and their relatively small size allows them to be assigned pretty readily if need be. But a lot of these methods don't necessarily need assignments. We can also tailor these NMR methods to look at both the native structural features of nucleic acids, that would be your aminos and your aromatics. But we can also look at the non-native chemistries and really leverage the advantages of like fluorine NMR as well as phosphorus NMR that you might not be able to, that you won't be able to with native nucleic acids necessarily in mAbs. And this last bullet point is kind of a future direction. Now that we've collected all of these NMR spectra, looking at the various structural features of the short oligonucleotide therapeutics, can we now use them in combination with different chemometric analysis to detect subtle changes in structure and purity? And that's going to be accomplished with force degradation studies, which are going to be taking place soon. So I'll keep you all posted. I'd like to take a moment just to thank some people that I've worked with. So obviously my postdoc mentors, Dr. Robert Brinson and Dr. John Marino, for all their help and guidance with this project. I'd also like to thank Christina Berganzo. She's done a lot of MD simulations and kind of that little cute little cartoon I show of the siRNA. She made that structure for me, which was very nice of her. And then I'd also like to thank our collaborators at UMBC, Jace Jones and Antron, who are developing orthogonal mass spec techniques to kind of complement the NMR measurements. And with that, I'd like to thank everyone for your attention, and I welcome any questions you may have for me. Thank you.
Thanks, Owen. Questions?
Very nice. I'm reminded of some stuff I did in this kind of area a long time ago, but in the diastereomers of the thiophosphates, are all the sites the thiophosphates, or are they scatter through the sequence?
So in the case of the phosphorothioates, it's only the termini, so the last 4 residues on either side.
Okay, yeah, because it amplifies the number of species so dramatically.
It's 2 to,
that's
yes,
pretty crazy,
exactly.
yeah. 2 to the n, yeah.
So that's 2 to the 8, givosarns 2 to the 6, and then for the phosphodiamidite morpholino, 2 to the 17.
Yeah.
So yes, it gets really complicated.
So is that the way the products that are actually approved are made, or just the way you designed it?
Nope, that is the way they are made.
That's the way they're designed, just at the ends.
There's a mixture. So some of them have it just at the ends, but some of the older ones, the whole thing was phosphorus.
Yeah, and that's just a zoo. Yeah.
Yeah.
Okay.
And I've actually spoke with people in industry, and they are not they don't seem too concerned with the distribution.
Yeah.
But after a few papers came out showing that the different variants have different levels of efficacy, now they're starting to pay more attention.
Yeah, that's a problem. And then one last follow-up. In the morpholino compounds, again, I saw something in your phosphorus spectra that reminded me of polysaccharides. So the terminal residue is resolved. Have you looked at doing sort of in-group quantitation to look at the purity and integrate that N-terminal phosphate compared to your bulk resonances as a quality control mechanism for the product itself? This used to be done in polysaccharides where you look at the N groups. and integrate across the whole thing. And it just looks like that's available here too.
Yeah, no, we haven't done that yet, but I'll definitely give that a look. Thank you.
Yeah, sure.
Great. We have another question.
Yes, I have a question about experiments for those oligonucleotides. Basically, these are for therapeutics. So it would be ideal if you could do the NMR experiments for the sample in serum. Of course, serum contains a lot of materials containing protons, but for your samples containing F19, probably those serum components doesn't matter, and you can measure a spectrum even for the oligonucleotide in serum. Have you tried such experiments?
You read my mind. Yeah, so that's actually one of the motivations for looking at fluorine, right, is it's background free. So there have been studies in the literature where they've literally injected, I think it was like a G quadruplex that had fluorine atoms into live cells and then run NMR on it. So yes, that is something we're looking into. We're going to look at, I won't all the way, but we're going to look at these siRNAs in the context of noisier systems with a lot of protonated excipients and whatnot. So yeah, that's a great idea. Thank you.
Thank you.
Great. Well, let's thank Owen again and everyone for the discussion. Okay, so our final speaker, Francesca Marassi, will be joining us remotely. Do we have you, Francesca?
Yes, can you hear me? Can anybody hear me?
We can hear you. Sorry that you couldn't be here in person, but it's great to have you.
Thank you. Can you see my presentation?
We can. You're good to go.
In the right mode?
It is.
Okay, perfect. Thank you very much. So I want to start out thanking Joanna, Len, and all of the other organizers for putting together this ENC after all this time. I really wish that I could be there, and I appreciate being able to do this on remotely on Zoom. So I'll tell you about some of the work that we've been doing to try and understand host pathogen interactions. And I'll show you a mix of experimental work that we've been doing together with computational approaches that have helped us and I think are useful also for the NMR community for improving structure determination. So as a way of introduction, this slide illustrates the scale of the pathogen that I will be talking about, this pathogen Yersinia pestis, relative to a bunch of other pandemics, including the present COVID-19 pandemic. And let me see if I can bring up my laser pointer. So this bacterium, Yersinia pestis, has been responsible for launching these huge plagues throughout history. You can see here a timeline and the magnitude of this, the magnitude of the pandemics over the years, documented by the CDC. And so understanding really how the bacterium continues to live with us and is able to both infect and survive in the host and cause massive and very rapid death is interesting. And it's interesting not only because of what we want to understand about the bacterium itself, but also because it relates to a bunch of interesting pathways within the human host that are responsible for things like innate immunity and cell adhesion and migration and coagulation and fibrinolysis. Okay, so this cartoon now illustrates this one key protein, AIL, attachment invasion locus, which sits on the outer membrane of Yersinia pestis. This is a gram-negative bacterium, so it has a cell envelope that's made up of an inner membrane protein and an outer membrane protein. And this outer membrane protein on its own is itself a virulence factor. So it's essential for the bacterium to express the pathogenicity that it does. Amongst the things that we discovered about this protein is the fact that it binds to vitronectin, VN, this abundant blood protein that circulates in our body, and is important for interacting with integrin ligands to promote host cell adhesion and invasion. It's important for regulating coagulation and fibrinolysis, and I won't go into all the pathways through which it does that. And it's also important for stabilizing the membrane attack complex, okay? So this sort of terminal assembly of the innate immune complement system that is important for actually punching holes into bacterial membranes, but if downregulated, will not do so. So this interaction is important for downregulating this, and through this, it promotes the ability of the bacterium to survive in serum or in blood and circulate and do all of the pathogenic things that it does to the body. So the question that we posed was, how molecularly does AL enable bacteria to survive and proliferate in the host environment? Because it's all nice to draw these cartoons, but as chemists and structural biologists, we want to understand the actual atomic level interactions through which this occurs. So through the years, we have done a good amount of NMR spectroscopy in a number of different systems. This is a membrane protein, and so we put a lot of effort into developing detergent-free samples where the protein would not only be structured but also functional with respect to ligand binding and activities. And what I'm showing you here are comparisons between solution NMR spectra, shown in red, and solid-state NMR spectra, shown in black, in which the protein was either incorporated in nanodiscs for solution NMR, so these are collected at 45 degrees C, or in detergent-free liposomes, actually both detergent-free systems, or in liposomes collected by solid-state NMR spectroscopy at 10 degrees C. And you can see that there's a lot of overlap between the resonances of, this is nitrogen proton correlation spectra, nitrogen carbon correlation spectra. There's a lot of overlap. There's very good line widths. This happens to be a relatively fast CP-HSQC experiment in which the proton line widths approach the range of 120 hertz. So what these types of spectra have allowed us to do has been to not only collect a number of restraints, and I'll show you more in just a second, but also obtain a number of assignments for the various regions of this beta barrel that allow us to map protein-protein and protein-ligand interactions. Amongst the experiments that we did was to take the nanodisc samples that we prepare for solution NMR. These are the very small nanodiscs developed by Gerhard Wagner with a small version of the membrane of the belt protein, of the ApoE protein that forms this double belt around the nanodisc. And so they give nice solution NMR spectra, but those are nevertheless limited by the size of the sample. And so they don't allow us to visualize all of the extracellular loop signals. And to do that, we decided to turn to solid-state NMR spectroscopy and do an experiment in which we took these soluble nanodiscs and effectively sedimented them in an air fuge. This is a tabletop ultra-fast centrifuge to produce a very dense sedimented yet soluble, it's like a very viscous plug of nanodisc that we could then transfer to an MAS rotor for solid state NMR spectroscopy. And so these spectra now illustrate the type of signals that we can obtain. These are carbon-carbon PDSD correlation signals that we can obtain for these samples compared to liposomes in black and mice cells in green. And these, again, allow us to obtain a number of assignments, but also to measure distance restraints for structure determination. So these illustrate some of the spectroscopy that we've done, that we can do with these types of samples. And these have allowed us now to determine structures both by solution NMR and nanodisc, solid state NMR and liposomes and nanodisc mix. So it turns out that in these types of samples, the loops, these extracellular loops, okay, there's 4 that protrude out of the bacterial membrane, appear highly dynamic. And several of these loop signals remain invisible in both solution and solid state NMR, presumably because they're undergoing dynamics that keeps them outside of the range of what's accessible by both NMR technologies. In addition to that, so we would like to access these loops because these are the actual functional end of the protein molecule that interact with things like vitronectin and other important ligands for functionality. So in addition to that, so this middle picture here illustrates what we all do in NMR spectroscopy. So regions that are not highly restrained, restraints are sparse, and we end up showing an ensemble of structures where it appears that the loops are highly dynamic, but actually this does not necessarily reflect that. It also reflects the fact that we don't have enough restraints, and that that we don't have enough restraints. So it's potentially not an accurate picture of what we would like to see in the membrane. So compounded with this is the fact that even though we've gone out of our way to not have detergent in the sample and produce samples that are, in lipids, in lipid environments with what we think are appropriate phospholipids, this is still very far away from the situation in situ, in vivo, where the actual bacterial outer membrane is, first of all, highly asymmetric, and this is a really nice MD simulation produced by Won-Pil Lim, who's done a lot of work parametrizing bacterial outer membranes. So they're highly asymmetric with an inner leaflet of phospholipids and an outer leaflet of lipopolysaccharides. It turns out that this membrane environment is actually very, very important for Yersinia pestis, because at the mammalian infection temperature of 37 degrees C, Yersinia produces both AIL, it upregulates it to a level that's about 30% of the outer membrane proteome, so it's highly expressed in the outer membrane, and it also produces a tetraacylated form of lipopolysaccharide that is poorly recognized by the immune system. And basically, this combination of AIL and the tetraacylated LPS conspire to allow very high titers of the bacteria to accumulate in the bloodstream. So this environment is important, and we would like to be able to look at the protein within it. So one of the first things that we did was to prepare nanodiscs for both solution and solid state NMR that not only incorporate phospholipids, but also incorporate this tetraacylated form of LPS that was extracted from Yersinia pestis by our collaborators. And this is work of Chandan Singh. So this is illustrating now AIL in nanodiscs that are free of LPS in black, or that incorporate Yersinia pestis LPS. And you can appreciate that there are a number of changes in chemical shifts. And what these do is they allow us to map AL LPS interaction sites. And indeed, they allowed us to localize the interaction sites to 2 clusters of basic residues along these sort of walls of the Yersinia pestis beta barrel. These, it turns out, using a number of solid-state NMR experiments that I won't show you here because I want to get to the computational work as well, also showed that they confer conformational order to the outer membrane loops that are exposed at the membrane surface. And so together, we have shown in a previous study that it's really this interaction between AL, shown in blue here as cartoon, and the LPS molecules along the sides of the loops that are important for conferring a number of properties to the bacterium. Okay, so together they display a competent conformation of AL for host ligand binding. They confer serum resistance. They're really important for membrane integrity, and they're important for antibiotic resistance. So the importance of this environment is really underscored by these experiments. So the ultimate goal is to really do NMR in a native microbial bacterial membrane. And so we did this recently, taking advantage of the fact that AL is so highly expressed at the infection temperature. James Kent developed an E. coli expression system, in this case, similar cell envelope structure, inner membrane and outer membrane, in which AL is enriched at the membrane surface and incorporates nitrogen and carbon isotopic labels. So this gel is basically showing that using this LIMO21 D3 expression system, we can isolate either cell envelopes right here, or even outer membranes alone. So cell envelope meaning the entire outer membrane, peptidoglycan periplasm and inner membrane shell, or just the outer membrane component with AL. So we can isolate these components and show that AL adopts a folded conformation in both of them. So these beta barrel proteins have this useful property of migrating differently on SDS page depending on whether they're folded or not. So, so with this type of sample, James could then acquire solid-state NMR spectra effectively of the protein incorporated in this native environment. Okay, so you just take the cell envelopes, pack them in the MAS rotor, and what these spectra are now these spectra are now comparing the data from the E. coli cell envelope in black and those that we obtained with liposomes. And again, nitrogen-carbon correlation, proton-nitrogen correlation spectra right here. These are exciting to us because they now allow us to, again, map subtle changes in chemical shifts that correlate with the environment. Okay, so here they are mapped as spheres along the structure. And interestingly, they not only map to the loops, but also to the body of the protein within the membrane, suggesting that it's more than just the LPS that sticks out to the membrane surface that affects the, that has an effect on the chemical environment of the protein. Okay, so these spectra also allow us to resolve signals from a number of sites, and these are shown in blue, some of the ones that you can detect from isoleucine, valine, alanine, serine, threonine, residues that, or signals that we have assigned previously and correlate well across these types of spectra. And also they, in gold, we can identify some non-AL, so non-protein bacterial cell envelope components, which are interesting for probing the system from the perspective of the membrane environment. And finally, I would say what's useful. Okay, so what's nice about having these kinds of systems is that we can now expose them to the host environment. So in this case, what we did was we took the sample, the NMR sample, and incubated it with normal human serum, okay, so blood basically, and looked for changes in the chemical shift pattern. And it's exciting that we can identify some changes, again, that correlate with the exposed loops and potentially some changes along the beta-barrel body. So we're in the process of sorting these out. What's nice about this is that the sample now can be used in parallel for solid-state NMR spectroscopy and for biological experiments. So again, without going into details, what we're showing here are 3 essential properties of this same sample that we use for NMR, and that is they confer the ability to survive in normal human serum. So they basically defeat the innate immunity of blood. These are E. coli bacteria that express our protein. They form pellicles. This is a major phenotype for many pathogenic bacteria. It's sort of the first step along the way of biofilm formation. And they pull down vitronectin, both from blood and material that we express recombinantly in the laboratory. So it's nice to have this set up, the system set up for doing both a spectroscopy and correlating with the activity. So having done all this, we're sort of faced with the issue that a lot of the NMR structure calculations that we do are performed in a purely repulsive force field, where we don't take into account things like electrostatic energy or even van der Waals attractive and repulsive energies. Tian in the lab has done work to develop an implicit water or lipid membrane solvation force field that basically takes the proteins from this gray area that's highly artificial to this colorful state where there can be either bathed in water or embedded in a native, in a lipid membrane. And so there's multiple advantages to this approach. I should say that, well, let me describe it first. Okay, so what I mean by this, okay, so typical force field is a simple repulsive potential. So your calculation will typically include a number of experimental restraints like dihedral angles, maybe from chemical shifts, NOE distances, PRE distances, dipolar coupling, CSAs, and so on. Whatever you can measure can go into the pot. It will contain some knowledge base terms like torsion dB, that's included in Explore NIH, radius of gyration, plane distances, what have you. And then it will have an energy that's really encoded within the force field that includes conformational terms like Bond's angle, improper dihedral angles, and dihedral angles, and a non-bonded interaction term. In this case, it's just a purely repulsive potential, and that has the advantage of speeding up the calculation tremendously, but also has the disadvantage that the environment is not at all realistic and has the potential for missing out some very important intramolecular interactions of the protein. So we have worked together with Charles Schwieters to develop this effective energy function that's essentially an implicit solvation potential for NMR structure calculation. So it's something that you find embedded with Explore NIH. And what this does is it basically replaces the non-bounded interaction terms with an energy function derived from the work of Lazaridis and Karplus that now incorporates a full Lennard-Jones type van der Waals term, an electrostatic term, and a solvation term. So some of the the potential is useful, okay, and what this is showing is a set of unrestrained now ND simulations that you can run with this term, and it's comparing the simulations run in EF in a purely electrostatic plus van der Waals alone, or the repel term, and you can see that EF does a pretty good job at maintaining the protein structure throughout at least 1,000 picosecond simulation. Okay, so here's a number of structures that are found together with the Explore NIH release and showing the benefit of using EF. So it's comparing the EF final structure together with the PDB experimental structure. The potential is also pretty useful for sustaining native protein structures in situations where there are sparse restraints. So this experiment took the NMR data from this manuscript on GB1 from Angela Gronenborn, and basically reduced look for the effect of the number of long-range restraints on the structural accuracy and precision. Okay, so the two plots are basically showing the completeness of long-range NOE data as a % of the total data, and the RMSD of either relative to the deposited structure, to the actual experimental structure determined with a full set of restraints, or the precision of the ensemble that's calculated. And it's comparing calculations done with repel, purely repulsive, or the effective energy function in implicit solvation. And you can see that in both cases, so both the accuracy and the precision are highly improved when a very sparse set of NOEs, like 4% complete, is used in the calculation. So we concluded from this that the potential directs the calculations towards a native fold. It improves structural accuracy and structural precision. And it also improves conformation. I'm not showing data about that in this slide, but all of the metrics that one can measure, with things like mole probability, for example, point to a much improved conformation of the protein. So these two pictures visually show what I just said. Okay, so here's the ensemble calculated with EF in red compared to the experimental structure or repel in gray. And you can see this much nicer, tighter bundle and better accuracy to the experimental structure with the sparse restraints. So because we're interested in a membrane protein here, and okay, I want to make sure that I don't go over. So because we're interested in membrane proteins, the next step was then introduce an implicit membrane model. So to take water and add implicit lipid and basically try to mimic this heterogeneous environment that's associated with a membrane, where the dielectric constant really ranges widely across the membrane profile. The amount of water, the concentration of water also ranges dramatically. Lateral pressure, fluidity, all of these parameters really vary from the outer aqueous regions of the membrane to the inner hydrophobic hydrocarbon core. And this is a picture taken from a review of Steve White basically showing how a representation of the membrane with the hydrocarbon core in the middle and the aqueous interfaces at the side. So, so we did this again following the Lazaridis protocol, but adapting it to the Explore NIH computational environment that where the functions could be used for relatively rapid structure calculations with experimental restraints. So in this setting, the membrane is modeled now as a function with the hydrophobic center here set at Z0. Okay, so this is the membrane as you would normally view it. And then this is the hydrocarbon center. So this function really describes the transition, okay, from a purely aqueous environment out here at the edges to a purely hydrophobic environment. And within the Explore NIH environment, you can set things like the bilayer hydrocarbon thickness. This is a parameter that can be set depending on your sample conditions. And you can also set the rate at which this function changes, depending on the type of lipid that you have. Using the system, we first showed that this structure, this X-ray structure in pink of bacterial rhodopsin can be embedded in the IMM or EF function of Explore NIH and can retain its not only structure, but membrane embedded orientation within it. This is a 1 nanosecond MD simulation within EF and IMX. And we also showed that this protein, FDCOAT protein, which is about a 50 residue protein produced by bacteriophage that spends part of its life cycle embedded in bacterial membranes, also retains this conformation and can be made to undergo MD simulations in the implicit membrane and to basically obtain a structure that has an improved RMSD precision. Okay, so here's EF compared to REPEL, and an improved correlation with the experimental dipolar couplings. Okay, so that's a validation basically. Okay, so it's a free simulation, but when you simulate it in this implicit membrane potential, the correlation to experimental restraints that are not used in the calculation is much improved, indicating to us that the model provides a better environment for basically these types of structures. Okay, so we've done these kinds of things with a number of embedded structures, including these Poseidon, which is a little antimicrobial peptide that sits on the membrane, and you can see that throughout the simulation, the peptide adopts the correct conformation at the membrane surface. With this transmembrane region of VPU, a protein from HIV, it starts out at the surface, but throughout the course of the simulation, it adopts a transmembrane helical conformation as expected from the protein and from the sequence. And with this structure of E. coli unpacks determined by Wagner and co-workers in nanodisk, where the protein also is at first embedded, we start out embedded in the membrane and then bounces up and down until it adopts this final conformation that remains embedded in the membrane. So with this protein, it sort of takes me back to this notion of the loops. Okay, so this is now looking at UNPACS. It's not ale, but it's a homologous protein to ale, the Yersinia pestis outer membrane protein. It also has 4 extracellular loops. In this case, they're not as long. UNPACS is not functional, but you'll notice that the structures calculated with REPEL end up giving you this fuzzy mess of loops, including structures that are simply not realistic because the loops end up sort of folding themselves back onto the beta barrel body of the protein and inserting themselves into the membrane. Whereas the structure calculated now with the implicit membrane potential is much tighter. Okay, so again, you see the effect of not having sufficient restraints for the loops, but at least the loops are now pointing out in the correct direction as expected for the protein. The other thing that that comes out of these types of calculations is, again, the correlation to experimental data. Now, this spectrum is a separated local field spectrum that we had obtained for OMPACs in DMPC bicels that had been aligned in the magnetic field so that the membrane plane is actually perpendicular to the magnetic field direction by the addition of ytterbium chloride. So a number of signals have been assigned by producing phenylalanine labeled protein. And so what the effect of EFX is that it basically embeds the protein in the membrane in such an orientation that if we back calculate the dipolar couplings and chemical shifts, by the way, chemical shift anisotropy here, from the orientation that results from EF, they correlate with the experimental data. So the calculated signals are shown as red circles, and the black is the experimental data. So again, this to us provides validation that the computational approach is useful for providing a more realistic environment for the sample that one is interested in looking at, together with providing higher precision and higher accuracy and conformational quality of the protein itself. So with this, I'm going to stop and acknowledge the people that who participated in the study. So specifically James Kent for developing the native sample, Chandan Singh for looking at the LPS in vitro samples, and Tian for developing EF. Our collaborators for providing LPS, for working with us on the microbiology and the NMR spectroscopy and so on. And basically summarize by saying that the goal of all of this is to really go towards the ability of doing experiments on these kinds of samples in maybe not in vivo, but in a real native environment that would allow us to probe the assembly, really, the membrane assembly from the point of view of the protein that we're studying, from the point of view of the environment, and ideally put it all together with functional data that will take us to the, to the key biological questions. So with that, I'll close. And thank you for your attention, and thank you for bearing with me remotely, and hope to see you all soon. Thank you.
Okay, thanks, Francesca. I'm afraid we've run over our time, so we do have to cut the discussion off today. But I want to thank all the speakers and all the attendees today. And Francesca, thanks for joining us remotely. Thank you all.
Thank you.